My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. Since the last time I've seen you,
Yeah,
you got married.
I did get married.
Amazing.
I think you got married since the last time I saw you as well, to be fair.
No, we've seen each other once, I think. We
Since then?
saw each other
Oh, that's true,
at our friend Adam's
Yes.
in January, December,
Yes.
somewhere around there.
Yeah.
So that was after I got married.
That
and
is
then,
true. Yeah, okay, no, you're right. Yeah.
And then you got married afterwards.
Yes.
How was it? How did
Uh,
the wedding go?
It was good. It could not really have gone wrong because our wedding was, we got to the registry office on the high street in Edinburgh, got married there at about 10 in the morning, and then we had nothing planned until 1 when we went to Toby Carvery, and then we went back to the house for coffee and cake afterwards with about 15 people. So
See, this all sounds really easy and simple,
yeah.
but we had a very, very similar plan, and yet everybody somehow randomly turned up at the job centre by mistake.
Well, see, that's because your choice of venue wasn't as easy to find as the
It
Toby
should have
Carvery.
been. It should have been. It was. They just hadn't updated
Yeah.
Google Maps and Apple Maps and
Yeah.
anything like that, so everybody just got pointed to the wrong
That was for
direction.
the registry office, right? Rather than the
Yeah, that's true.
So at a registry office was me, my wife, 2 witnesses, and Adam, who was doing the photos, same as he did
Yes.
at your wedding.
Yes. The one person who was at both of our
He was
weddings.
the only person who was nearly late because his motorbike wouldn't start in the morning because it was so frosty.
Ah.
And then he had to bring the van instead, and that meant he got stuck in traffic.
A little bit of an intro.
Uh-huh.
You are Dr. Oliver Brown.
Yes.
You did your PhD at Heriot Watts,
I
same
did.
as me. We've
Yeah.
known each other for, I don't want to think how many years, too many.
How do you feel about swearing in your podcast?
Minimal. So let's,
Shit.
yeah.
So you're saying the more I swear, the more editing you have to do.
yeah, please don't.
Right. So anyway, we've known each other too flipping long. 2009,
Yes, it must be, because we
4th of September, I want to say.
did our undergraduate degrees together and then did our PhDs at the same time at Heriot Watts and then disappeared in different directions afterwards, although still both in Scotland, so still both in the same area. And you are now at the EPCC.
Yep.
And have a Chancellor's Fellowship with the University of Edinburgh as part of the Quantum Software Lab.
Chancellor's Fellowship is independent of the Quantum Software Lab, but I am in the Quantum Software Lab, yes.
Okay.
Yeah, so my Chancellor's Fellowship is just with EPCC, doing whatever I want, that being the nature of a fellowship, really. But yes, I'm a co-I of the Quantum Software Lab. That's probably well, if you're in academia and you know what a co-investigator is, that's probably the easiest way to describe it.
Yeah. I had Nick on a few days ago.
Yeah.
So Nicholas Westerberg, who we both know.
Yeah.
And he had exactly the same message about fellowships. It's like, oh, I've got a fellowship. I do what I want.
Yeah.
So you're both doing a great job of advertising the use of people's money here.
Well, I mean, okay, but to be fair, what I want is to research how quantum computing and HPC will interact at some point in the future, in particular in order to support scientific computing applications using quantum computers as accelerators. So, there's a public good buried somewhere in there.
Yeah, that's true.
It's just, and you needs to be something like that to get a fellowship.
That is true. It needs to be in some way useful.
If it was really like I had a fellowship to do whatever I want, I would be sitting at home playing video games all day, which I only get to do on leave at the moment, on weekends. Yeah. So, to be fair, it's what I want in the professional sphere.
Yeah.
Not actually
not
what
just
I want to do.
anything that you want.
You know how some academics have this thing where they're retired, but they keep going?
Yep. That's not you.
No. I'm now 34. I've got another 34 years to go, as long as the retirement age stays the same. You can believe that I will be gone.
Yeah. Anyway, on to something science related.
Yes.
So you mentioned HPC before.
Yep.
So just to make sure we got acronyms covered, that's
All right.
high performance
It
computing.
is indeed high performance computing, which quantum computing is not, just incidentally.
Yes. and we'll get to that.
Yeah.
But I guess the bottom line is you're very much a computing person.
Yes.
So here for the quantum computing aspect.
Yep.
It is February
It is.
2025.
Yeah.
Where the hell is my quantum computer?
Oh, you can get one in the cloud if you want. Yeah.
Yeah?
How much money have you got?
On me? Very little.
Yeah, well, then no, you can't. But one could, with enough money, get access to a quantum computer in the cloud. You can get free access to. We've been using the free minute a month, I think it is, you get out of D-Wave for like their developer access for some projects. I don't know if that's in their licensing terms.
Really carefully select what you're going to do with that minute.
Well, no, a minute gets you quite far, actually.
Okay.
Because it takes like, so for the runs we've been doing, it takes 4 or 5 seconds.
Oh, wow. Okay.
Yeah. So that's a quantum annealer, which is a particular type of quantum computing. Things that are a bit harder for the digital, the things that everyone thinks of, which are the superconducting digital quantum computers. But they absolutely exist. They're there. They're available commercially. They don't, and some people may disagree with me on this. They don't do anything useful yet, and they won't for a while. Jensen Huang said that, and it completely tanked a bunch of quantum computing stocks. So I expect the same to happen.
Oh yeah,
when this podcast gets out. But I mean, basically, I just think that so some of it comes down to people have different definitions of what something useful is.
Yep.
So if you ask me, something useful is scientific computing, because I don't really care about industry making lots of money, because I don't get any of that money. I don't get any money from scientific computing either, but at least it is what I ended up at EPCC to do, was to help scientists solve their problems with computers. That application is a very long way away, because although there are some applications in scientific computing that are a fairly natural fit for a quantum computer, they all require a really, really good quantum computer. And more importantly, from an academic perspective, a really, really good quantum computer that's free to access. So
let's touch a little bit on what quantum computers really are and what they're doing. Because you kind of mentioned this a little bit, but it'd be good to go into a bit more detail. Yeah. So a quantum computer is obviously not going to do the same job as a conventional computer. As in, at the minute we walk around with typical conventional computers in our pocket all the time in the form of mobile phones. Quantum computers are never going to get to that point, or at least it's not going to do the same job.
Yeah.
So what are the jobs that quantum computers are going to do? Where are they going to be used?
So my opinion on this is the following. Any problem that you can solve on a laptop, you should continue to solve on a laptop in perpetuity. Because quantum computers tend to do well at a very large scale. So quantum algorithms, the things that you would run on a quantum computer that solve some problem, are typically good because of the scaling properties that they have. And by that I mean, for very large input sizes, they will do a better job than classical computer potentially. So the big killer application for quantum computing historically has been Shor's algorithm, which is an algorithm for doing something fundamentally boring. It finds prime factors, or prime factors of large semi-primes, right? So this would be completely uninteresting, except we happen to have based all of computer security on it for the last few decades. But it doesn't really advance human knowledge in any way to be able to do this. But whatever, Shor's algorithm is an algorithm that is exponentially faster for doing that than the best classical algorithm. The thing is, the gap between an algorithmic complexity and an actual implementation is the entire field of HPC research. Going from here's an algorithm that's faster to actually implementing it in a way that you achieve that speed up is a whole different problem. And all that a lot of quantum algorithms give you is that algorithmic improvement. So you need to be able to actually implement it in a way that it really is faster. And that is hard. And that is what a lot of the hardware vendors are essentially trying to do, is to try and create hardware that is good enough that you actually realize that benefit. Yep. But even so, the point is that benefit appears as you start to move to very large input sizes, because when we say that it's exponentially faster, what we mean is the scaling with the input size is exponentially better in this case.
Okay.
So generally speaking, for a small input size, you'll see no discernible benefit, because exponentially faster of not much time is completely pointless.
Yeah.
And it's an enormous amount of effort to put into doing something that runs in a minute to make it run in 10 seconds. No one cares. On the other hand, when you have a very large problem, you may well see a much more interesting benefit. And there's also some potential for there to be higher accuracy solutions for things like where you're trying to solve a quantum problem and do quantum simulation, stuff like that. But there are also a lot of caveats on those around measurement, which is a fundamental problem in quantum in general that doesn't get any better for quantum computing. So there's lots and lots of caveats around what you can and can't actually do with the quantum computer and what you'd want to do. But in general, my feeling is that you will see the most benefit when you look at very large problem sizes, i.e. the sorts of things that we currently solve using HPC systems, not the kind of things that we currently solve using laptops, desktops, individual workstations, or anything around that small size. But instead, we'll see the bigger problems being tackled by quantum.
Can you give us a couple of examples of those sorts of large problems, just so we can get a sense of idea of scale?
So, as you know, I've come today from a meeting at Strathclyde University with Professor Viv Kendon, where we are talking about the QCI3 hub, which is a new quantum technology hub, and the work packages there that we have in the applications theme are around fluid simulation. Computational fluid dynamics is a huge proportion of the usage of things like ARCH2, the UK's national supercomputer, as is quantum chemistry and molecular modeling and materials physics. It's also a huge proportion. In fact, the biggest users of ARCH2 are people running a code called VASP, which is some molecular modeling thing, I think. But that kind of quantum physics and chemistry problem, those take a lot of computational resources and are the kind of things that quantum computing may well be a good fit for. And then separately, there is also the kind of annealing type problem, which is when you're looking at binary optimization problems. That's something that quantum computers should be able to do well, but it's very hard in practice. However, that hardware is a lot more mature, potentially, than some of the digital quantum computing stuff. So you can get better results right now out of D-Wave, I think, than you can, say, any of the circuit model things.
So you've mentioned quantum annealing a couple of times now, and specifically mentioned D-Wave.
Yes.
So what is the difference between those kind of systems and the superconducting systems that you were talking about before? So in other words, what we might think of as, let's say, true quantum computing, if that's the right terminology.
Digital quantum computing, I'm sure, is what
people
the likes of D-Wave and QERA would prefer you to refer to it as. Yeah, so digital quantum computing is somewhat more fundamental in that basically what you have there is a quantum state vector that you apply operations to until it gets into some state that is whatever you need it to be, and then you measure it. And that's the answer to your problem, you hope. What quantum annealers do is find ground states of quantum systems by cooling them down. And you hope that the ground state is the answer to your problem, whatever that may have been. Now, that's a really obvious link if your question was, what is the ground state of this quantum system? Fine.
So before we go any further, by ground state, you mean the lowest energy state for a specific quantum system that I'm interested in.
Yes.
So this is a really, really specific thing that people would be looking for.
Indeed. However, numerically speaking, that's the same thing as solving an eigenvalue problem, which is, again, if you're not familiar with linear algebra, eigenvalue problems are just very common across all spheres of science and engineering, really.
And you can think about that as finding the simplest solution, let's say, to a complex mathematical problem.
So in essence, anything that looks like an eigenvalue problem you could do on a quantum computer or a quantum annealer. But it's a way of solving optimization problems where you're looking for, in this case, the lowest energy. And the trick actually is just to map your optimization problem onto what's called the Hamiltonian, which describes the free energy of a quantum system. And then you cool it down, get the ground state out, boom, there's your answer. Even better if the answer that you're looking for was in fact a bit string. So quite often annealers right now are being used for binary optimization problems, which are, I have a number of binary variables, what gives me the most optimal answer out of these 0 and 1 choices I can make. And there's an entire framework for that called Quantum Unconstrained Binary Optimization, or QUBO. And the idea is really you should be able to fling any QUBO problem onto an annealing bit of hardware, get the answer out. And it is much harder than that in practice. But those devices do, generally speaking, work. They're available. You can try them out. They are, in my experience, for the problems I've been looking at, not faster than trying to do the same thing classically. But that's sort of okay. They have very nice scaling properties, actually, so far in our experience. Because naively, right, if I have an annealer, every time I add 1 qubit, I double the space of wrong answers, and I still only have 1 right one. Because of the way quantum works. But so far, we do not see that the scaling is exponential in the number of qubits that we require, actually, in the runtime it takes, which suggests that their sampling is somewhat better than random chance, which is a good start. In fact, it's fairly flat, so we can drastically increase the number of qubits we're using and still basically get the same runtime out to find a solution. If it finds the solution, that tends to be the hard part.
Yep. Let's go right back to basics, because you started mentioning qubits.
Oh, yeah.
So very, very beginning.
Yeah.
Classical computers use bits,
Yep.
binary digits, so 0 or 1,
Yep.
whereas quantum computers, let's say that the power behind a quantum computer is the fact that it uses these quantum bits, qubits. Could you explain to us, what is a qubit?
So a qubit, I said, is a quantum bit, and really that means from my perspective, there are two important features. One, superposition. So a qubit can be not just in 0 or 1, but in 0 and 1 in an essentially arbitrary amount of each. It's a complex number that says, there is this much 0 and this much 1. So you can mix the two. And that actually looks exactly like analog computing, which we already don't use. So that in itself is not enough for a quantum computer to be more powerful. The actual extra power you get out of a quantum computer is in interference effect, really, and entanglement. So you can create states on a quantum computer which cannot exist in a classical one. These are called entangled states. And so the simplest example of one of those is for 2 qubits, the state 0, 0 plus 1, 1.
Yep.
With no contribution from 0, 1 or 1, 0. That is not something that you can make happen classically, because you will always get a bit of 0, 1 and 1, 0 in there. But it can happen in a quantum computer, and it can happen in a quantum computer because you can have interference effects cancel out those states. And that is where the power of a quantum computer comes in. And the hard part is just that those are the hardest states to prepare and do anything with. So a lot of decades worth of quantum control are required to be able to manipulate these things well enough that we can really use those for computing. And that is where we're now at. The problem is that we're not able to do it well enough that we don't introduce a load of noise.
So reading between the lines a little bit, 1 qubit gives you this superposition of 0 and 1. Same as analog computing. So not necessarily giving you a big advantage, but the real power is in, like you said, entanglement and quantum interference effects, which necessarily means that you need more than 1 qubit. In other words, you need multiple qubits are interacting.
Absolutely, in order to do any kind of quantum computation where you may see some kind of advantage. And then the other thing you have to watch out for if you're trying to use a quantum computer is measurement, which we sort of already mentioned. But whenever I measure a quantum bit, I get 0, 1. I do not get the superposition state out. I just get, with some probability, the answer 0 or the answer 1.
So you basically end up with a classical measurement at the end of the day. You can't do a quantum measurement and use that to interact with the real world. At some point, you've got to interact with classical mechanics.
And that makes extracting the answer quite hard, depending on how you encoded it. So in practice, you often need to run things multiple times and build up a statistical picture of what the solutions it finds are, and infer from that the answer to your problem. But that, I think, is one of the bigger challenges facing quantum computing, is that you can come up with a really sophisticated way of getting the state vector to represent the solution to your problem, and the problem is getting at it, because you cannot read quantum information. You can only read classical information. So you're basically still looking at the answer, or a partial version of the answer, whenever you perform a measurement, and that creates all kinds of problems for you.
So you can create let's say, a quantum algorithm that will give you the solution that you're looking for, but it's actually accessing the solution that's problematic part.
So if you're lucky, then all you really need is not the quantum state itself, but some global property of it. That's the best possible scenario, because then you can evaluate that somewhat efficiently. However, that may not be the case. Depends entirely on your algorithm. A lot depends not just on the algorithm, but actually how you encode data in the first place into the problem. At the moment, often people focus on trying to minimize the number of qubits that are required, because there aren't that many available, compared to, say, a classical computer where I have a lot of bits.
Yes.
A lot.
So just to kind of like throw out scales there, I mean, I don't actually have a number that I could put to how many bits a classical computer typically is using, but it's many millions.
My desktop, because I spend too much money on computers, has 32 gigabytes of RAM, which is 32. It's approximately 32 times 10 to the 9 bytes, and a byte is 8 bits. It's actually not that, because there's a difference between a gigabyte, which is a base 10 number, and a gigabyte, which is a base 2 number, but let's ignore that for now. It's somewhere in that region. A single node of a machine like Archer 2 has 256 gigabytes of memory available per node, and then it's got a lot of nodes, 5,000 or so.
So many trillions that you have access to.
Meanwhile, a very large quantum computer might have 100 or so qubits.
Big jump.
And a qubit is worth a lot more than a bit when it comes to computing. However, at output time, when you measure it, 1 qubit is worth 1 bit. You can extract precisely 1 bit of information per qubit.
Yeah.
Always. It's the Halevo bound, and that means that it's quite difficult then to find a problem where you need minimal data in, data out, but can do a lot in the middle. Right? That's really what you're looking for at the moment.
So kind of summarizing, you can build systems where the system itself will interact very, very quickly, will do computations very, very quickly, and potentially do lots of stuff in parallel. But what you struggle with is getting the initial data in and the final data out.
Yeah.
That's the speed bottleneck for actually using a quantum computer.
Also coming out with algorithms to do anything useful on these things, because as a software engineer, I'm very used to sitting down and I can write some C++, or if I'm feeling particularly lazy, maybe some Python, and I'll have all kinds of high-level data structures that I can play with to construct my algorithm, or to turn my algorithm into a piece of functioning software that implements it. I define functions and high-level data structures, and I work with those. None of those exist for quantum computers because we don't have 64-bit words to play with. We have maybe 64 qubits in total, so I need to be a lot more efficient while I'm doing. And actually, the way that I describe the series of operations that I need to carry out on those qubits is at the gate level. So I say I'm going to apply this transformation to the state vector by modifying this qubit in this way with what we call a gate. It's not really a gate in the classical sense, because classically circuits are physical spatial descriptions where I'm connecting, voltages up through some sort of electronics.
Yeah. So for the classical case, I mean, a gate is going down to the single transistor level pretty much, right?
Exactly. Yeah. Well, a few transistors, but it's very low number of transistors. This is way low level. Whereas what I do typically is just, I work with data types like a floating point number or an integer. At the quantum level, we're very much working on individual qubits by applying gates to them and transforming them. So basically, designing a quantum algorithm is just a linear algebra problem that you're trying to solve. And then you have to implement it that way as well. So I take my qubits and I transform them in some way, and then I measure them. And I may have to repeat this. I may have mid-circuit measurements that tell me to do other things. But it's an extremely low-level way of designing algorithms and then of actually implementing them, which makes everything harder.
Yeah, of course.
So one day we would hope that there will be nice high-level quantum programming languages, but they certainly do not exist right now. Now, it's weird because a lot of the time, actually, the interface you get to a quantum computer is in Python. So on the face of it, that's a nice, easy-to-use high-level programming language. But what you're doing with that nice high-level programming language is designing a circuit.
Yeah.
So you have to remember, for example, whether qubit 0 is your highest qubit or your lowest qubit, and exactly what that one is encoding at both input and output. And they can be different.
Yep.
So you might encode some data in at the start, and then the way that you read them out is completely different because of the transformations you've made in between. And those are completely different for every single algorithm which you might want to run.
I guess it's important to point out that when for people that don't have that much experience with computer programming, we don't go anywhere near this level of detail when we interact with classical computer programming. Everything has got its...
Some people do. Some people are still out there writing assembly, but not me.
Not most people, not the vast majority of people.
Yes. So we're very much, I always describe it as like quantum hardware is somewhere around the 1970s, 1980s in comparison to classical hardware. We've gotten through the valve tube era, just about, but we don't have... So in classical hardware, at a certain point, which I don't remember exactly when, sometime in the 1980s, I think, might have been the 70s, everything settled onto a particular type of transistor. Mm-hmm. And all hardware is now made out of that particular type of transistor, generally speaking. So all of these like low-level concerns are gone, because we just have... I mean, even as late as the 90s, you would have to worry about having compilers for particular architectures. Now, almost everything that I interact with is using a particular instruction set. So we just use the same compilers everywhere, and it doesn't matter. There are some other architectures, there's things like ARM, uses different compilers, but basically, I don't care. What I do is I write some C code, C++ or Python, and then it's up to whoever has sold me the hardware to make sure that that code will run on their hardware. Whereas in the quantum world, we are nowhere near that. We are still very much, there's 10 different types of hardware. There's completely different computational paradigms out there, because there's photonic, annealing, and circuit model quantum computing all at play. And they may be used for completely different things, and we have to worry about all of them. But the software situation is much worse. We're basically in the 1940s for software, because we're still faffing around designing circuits rather than writing code, and we will be for some time.
So probably an important thing to point out is that within the realm of quantum computing, you obviously don't have everybody doing the same thing, right? Mm-hmm. You've got this camp of people who are developing the hardware, and then you've got a camp of people like yourself who are writing the software. Yeah. What the hell are you going to do with the quantum computer when you actually got it? Yeah. So how much do you actually have to bear in mind these different hardware architectures? Like, if you're having a conversation with someone who works with superconductors, how is that different to someone that works with photonics, for example?
Yeah. Well, in that case, so like boson sampling is a completely different... It's the one actually, despite my background coming from a uni that's all lasers, is the one I understand the least. So so right now, I don't know exactly how I would write code for a bosonic sampling quantum computer, or a boson sampling quantum computer. If it's for circuits, then we or superconductor, not superconductor. If it's digital quantum computing, then we design a circuit. And usually, basically, we have to use whatever the hardware vendor provides as an interface. And it's typically a Python library, right? Some of my work is around designing interfaces with the hardware that are more focused on supporting high-performance computing, therefore probably not in Python. But that's very sort of early-stage work. But the difference basically is completely different, right? Because then you've got annealing, which is a more specific device that solves a particular set of problems. So we can't just design a general circuit algorithm and throw it on there. Instead, we start from a different place where we go, okay, I've got a QUBO, say, and it's quantum unconstrained binary optimization I'm trying to solve, and I just want to provide the Q matrix. However, you can also get analog quantum computers that do Hamiltonian simulation. If you speak to kind of the Rydberg atom people, they can basically do any of those things. But the question is, what interfaces do they provide you, the user, to actually tell them that you want them to do that with their hardware? Yeah. That's the interesting question from my perspective. But basically the answer is, the conversation I have is always basically the same, where I'm saying, can we not have to rewrite all of our code just to use your platform, right? But at the moment, there are fairly good reasons, quite often, why you do have to do exactly that.
Yeah. So you mentioned kind of like how slow these things can move, and 10 years is a really good time frame to look at, because we've also got these targets that have been set by the UK government, essentially, the so-called the UK quantum missions. Yeah. And the first one of those, because they're numbered 1 to 5, first one is by 2035, we, in essence, will have a useful quantum computer. Yes. So in 10 years, we should have that quantum computer that I've been describing.
Yes. I think, as I say, the question is useful for what? Yeah. And that is you're always going to get a different answer depending on who you ask. I do believe that in 10 years we may have a quantum computer that's capable of doing something that someone is willing to pay for, right? I think that is possible. I do not think that someone will be the academic or scientific computing community, because they're generally speaking not willing to pay for anything. But I think, it's possible that will happen, although we'll see.
Are there any particular sectors that kind of jump out as to being willing to pay and actually needing the advantage?
Well, okay, I don't want to comment on needing the advantage, but there are certainly sectors that are willing to pay. I think probably the big two that a lot of the vendors are focusing on for sensible reasons are pharmaceuticals and finance.
Yeah.
Finance has a lot of optimization problems that fit somewhat neatly into that binary optimization mold. Do they have big enough optimization problems? Don't know, but it's possible. And then pharmaceuticals is basically mostly molecular and like chemical,
like discovery
problems,
of new molecules, that kind of thing.
Or either optimization problems or
designing drugs,
exactly,
that sort of
things like that.
Problem.
But basically, fundamentally quantum problems, at least at the low level. So there should be a good link there, and it's a well-funded industry, basically, right? So they've got the money to. So a lot of these industries will have something called horizon scanning, where they are looking not at things that they're going to be doing tomorrow or they're going to enter their production workloads, but things that will help them stay ahead of competition in 10, 20 years' time. And if you're in one of those industries, it does make sense to be looking at quantum now. Two reasons. One, because of the problem I already mentioned of, it's one thing to have a novel bit of hardware and quite another to actually exploit it. And basically, you need a lot of software work in between to make that happen. But secondly, also because if your application is one of the ones, if you've got an industry that's willing to pay for quantum computing, and you've got an application where it actually provides some benefit, or may provide some benefit, it's much more likely to provide benefit if the hardware vendors start working on your application now.
Yeah.
In some level, at this point, you can kind of sculpt the direction that the hardware takes, because it's looking. Quantum computing is a solution looking for a problem. So if you can give them a problem where there's actually some money to be found, it's quite likely that people will focus on trying to make it work.
Does that mean that some of these physical architectures would naturally die off in that case, and so would rise to the surface as being the dominant ones?
Oh yeah, I expect so. Yeah, I can't envisage a situation where, like in 100 years' time, there are still 10 different physical ways of implementing a qubit that are widespread.
Yep.
I don't know. It's not clear to me that we will see the same dominance that, say, CMOS transistors have in the classical computing space for a particular architecture. And I would be surprised if there isn't still some different modes of quantum computing. So I expect annealers will still exist alongside digital quantum computers.
Yep.
Because basically trying to do annealing on a digital quantum computer is rubbish.
And it's like you said before, like it's not like the classical computer would be disappearing either. You've got different tools for different tasks.
Indeed, yeah, that's a misunderstanding that I do sometimes have to talk about with people. So one of the fundamental theorems of quantum physics is the no cloning theorem, and that says you cannot copy quantum information, you can only move it. And now I ask you how many operations you do on your computer every day that require copying data. You do not want to implement those on a quantum computer. You should not implement those on a quantum computer. There is no such thing as a completely independent quantum computer, because A, you can't copy any data, and that's really annoying for most computing tasks. And B, you or I cannot interpret or do anything with quantum information, or even access it. We only interact with classical information. Ergo, there must be some classical computing somewhere in that loop.
Yeah.
And it does not make sense, really, for that classical computer to be just a tiny microcontroller.
Yep. Whilst I have you, what is your favorite random science fact?
Yeah, okay. So you asked me to think of one, and I did have to give it a think. So 4 equations of light, who wrote those?
That would be Maxwell.
Incorrect. They are Oliver Heaviside's equations of light, simplified from Maxwell's original 20. But the 4 that everyone thinks of and calls Maxwell's equations of light are actually Heaviside's version of them.
Huh.
And he independently developed the differential calculus required to write them in that form. So Oliver Heaviside was a British physicist from the late 19th century, and he worked for the post office, and a lot of his work was on electromagnetism, particularly for things like telegraphs. So transmission line theory is Heaviside's. And he, I think, is still greatly underappreciated for his contributions to electromagnetism, partly because he worked at the post office and didn't get on with his boss. So there was a disagreement about what was optimal for transmission lines that basically caused his boss to try and bury his work a lot of the time, and he became quite eccentric in his old age as well. But I think we should acknowledge more Oliver Heaviside's contributions to electromagnetic theory, and in particular, when you see those 4 lovely equations, remember that those are the Maxwell-Heaviside equations, not just Maxwell's. Yeah, and that's my favorite random science fact.
I feel like we don't teach enough history of science when we study things like physics degrees. It's very much, here is the science, here's the equations of how to solve them, go away and solve some other problems related to this, but not anything about the history, about how these things came to light.
Here's my big gripe about the way that we do that as well. As like, so you'll introduce some theory, right? And it's maybe like Einstein's theory of relativity. It's not just Einstein's theory of relativity. Lots of people worked on that. And so a lot of science is done very incrementally, and you don't really see that until you actually become a researcher. You know, you spend your 3 or 4 years of your PhD doing basically complete rubbish, right? As far as you're concerned, you get to the end, you're like, what was the point in any of that? Basically, that's how science has always worked. It's just that we have things like the Nobel Prizes, and generally like popular media tends to portray these geniuses having these incredible ideas that change the world, but that is really not how science works, generally speaking. It's much more, I mean, if you look back at the like history of physics in the early 20th century in particular, it's basically a lot of people arguing a lot about what is right and what is wrong, until an experimentalist comes along and goes, well, this matches that theory and not that one. But also a lot of the theories that people developed were basically incrementally building on other people's work. And it's always that way in science, but we tend to go, oh yeah, this is Dave's theory and look how he's changed the world. But you know, it's never just Dave. And I think we need to acknowledge that more.
Well, now I'm expecting in like 30 years' time, next round of Nobel Prizes will be announced, and you'll be sitting there going, son of a bitch took that from my thesis.
You know, someone's actually read my thesis. Someone told me that they...
Oh, really?
Yeah. I was like, why? Why have you done this?
On that note, thank you for your time, Ollie.
You're
It's
welcome.
a pleasure as always. Thank you.
Great.
You've reached the end of the podcast, which probably means that you enjoyed what you're listening to. So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.